Maxwell's relations. Unless anybody wants to stop me with some questions, but if I don't look up, I won't know, will I? I will look up in a second. And these Maxwell's relations are these somewhat cryptic things that are related to the fact that mixed partials are equal to each other. So the example I did, we finished on, is I go back to my du is T ds minus P dv. And this tells me that partial u, partial s, and constant v is t, and partial u, partial v, and constant s is minus p. So that's what I immediately read off here, okay? And if I use this fact that if I take the mixed partial, I'm being not totally careful by putting, and I did it last time, like hold this constant, take this derivative, then take the derivative. If we do that, then if I take the derivative of t with respect, so what I do is let me sort of give some advice about this, and I'll say this again, but let's say I saw, so I see that I have something, and I have an s and a v, and the s is a derivative, and the v isn't, okay? But the s and the v, they show up downstairs. Like if in the basement of the expression, there's an s and there's a v, you should, and if you see it in other, I'll explain what I mean in a little bit. If you see that, you should think, oh, s and v, those are the independent variables. What function has s and v as independent variables? U, the function u, right? Because we have floating around. U is a function of s and v, and that's why we can take that. And if I do this, if I take, oops. So here I've taken the derivative with respect to s and held v constant. Now if I take t and now take the derivative with respect to v and hold s constant, that's what I'm trying to say. So I have my t dt dv at constant s. That's going to be equal to taking this thing and taking the derivative then with s and holding v constant. So I've got, and there's a minus dp ds at constant v, minus. Let me clean that minus up because I want to draw attention to it. So here, like if I see this, let's say hypothetically, somebody asks you to, this could be an exam question. What is partial t, partial v at constant s equal to? The way I would answer this is I'd see these things, and I'd say, aha, u of s and v is relevant. And so I would go and look at this equation here, and I would note these things, and then I'd say, oh, there we go. There's the t. And then I would realize, I would use Maxwell's relations. And every function, u, a, h, g, they all have a pair of Maxwell's relations. So there ain't that many of them. And so I would contend that a Maxwell's relation question would be a good one to get because it's easy. as long as you know how to do them, you know. And do you memorize these things? Please no, don't do that. Although the graduate textbook has some elaborate way of memorizing these things. I guess back in the old days, when you couldn't say, "Hey Siri, you know, what are the Maxwells," or something like that, then people would have to keep all this stuff in their head. But it's better not to do that. You know, on any exam, right? Things like this will be there for you, okay? And from that, I would hope that you would be able to figure that out. Okay, so you need to know. You need to know sort of this means that there's this function, and the thing multiplying ds is that, and the thing multiplying dv is that. That's fair enough. And so once you know that, then you have everything you need to do to answer this question. You know, you need a little time, of course, but you know, on a final especially, there's plenty of that. Now, I point this out because that minus sign, there's a mistake. Siri's talking to me. There's a mistake in the book. So when you read the section in the book, in the text, they forget the minus sign. Okay? So even Atkins, the great Atkins, can have his foibles. Okay. So, you know, we can do this game for A and H, but for G, as a function of T and P, we know dg is minus s dt plus v dp, and from that we know minus partial s partial p at constant t equals partial v partial t constant p. And why do I know that? Because minus s is partial g partial t at constant p, and v is partial g partial p constant t, right? So that implies these things, and then the mixed partials imply that. So if I gave you minus partial s partial p at constant t as something that I wanted you to figure out what it was equal to, again, I would see there's a p here and there's a t here, and then I would think, temperature and pressure, it's got to be G, and it's got this. And if I didn't know that, then on the front of the exam I would see this, and that would tell me what road to go down. I would extract this from looking at this, just by knowing a little calculus is a dangerous thing, but you know, I know relatively little myself, so I would, but I had enough to get that, and then I would get the mixed partial here. I don't know about you, but if I look, let's say I gave you the left-hand side, right? If I start, and let's say you forgot there was this thing called Maxwell's relations, could easily happen. And so, you know, you're in that state of desperation, fight or flight, you know, elevated heart rate, all the things that characterize being a student. And you're, how do I do this? How do I do this? So you start looking at it and trying to figure it out. To me, it's not very intuitive, right? I don't really have an intuition for that object. I have to rely on the math of this bridge, you know, sort of bridge between math and ideas, physics, to do it. And the right way to do it is to fall back on the Maxwells. Let's review a little bit and check this. Let's check this out. For what system should we use? I know. Let's use the ideal gas. Okay, and so we have, you know, n equals 1, and that C being 3/2, monoatomic ideal gas, right? So I know that PV equals RT. So I've got that, and I know I have an S here. So why I write this down. Why did I write that down? Because I'm desperate. It's an exam. I write everything I know. But it is true for the ideal gas, and it happens to be useful because I look over here, and I see there's a V, a T, and a P. So PV equals RT. Very promising place to work, at least on the right-hand side. But what about the left-hand side? I know that S equals S naught plus R log T over T naught to the 3/2 V over V naught. Okay, but this is S as a function of T and V, but I got to be careful, okay? You got to be careful. You got to do this the right way. I need to find S as a function of T and P, and I need to take the derivative with respect to P and a holding T constant. And both T and V, they depend on P, so you gotta be, well, T, if T is an independent variable, it doesn't. But V depends on T and P, right? And if I want, then you could use chain rule to do it, I suppose. But let's find S as a function of T and P, and then I can do it. Okay, if I have S as a function of T and P, then I can hold one constant and take the derivative with respect to the other. Okay, so I need to get rid of V over V naught, right? And that is equal to T over T naught. Let's get it right. So, P naught V naught over PV equals RT naught over RT. Or, vice versa. So I can get this, right? So I can rearrange this. Let's check myself. I'm always, let's make sure we're, so this allows me to express V over V naught as a function. Like I said, V was a function of T and P. There you go. That's what it is. Okay, so I can substitute that. Here's my T over T naught to the 3/2. And then I have V over V naught, which is going to be, everybody has well, not everybody, but everybody that I talk to seems to have an iPad, and they use it for everything, and they have beautiful handwriting on this iPad. I don't know how they do it, but I'm going to try. And so there I put in, this is my V over V naught, right? So this came in here. And so my S is equal to S naught plus R log T over T naught to the 5/2 P naught over P. That's what it is. So S of T and P. So V is a function of T and P is equal to RT over P, right? Partial V, partial T, constant P, right, is what we want to calculate, is equal to R over P. And partial S, partial P, constant T equals, and so So you could write this. You could say S is equal to some constant minus R log P. So notice that I have a P naught over P in the logarithm, and so I have a 1 over P in the logarithm. And I don't like doing this because of units. You know how I go on and on about that. But I could do it mathematically. I could have everything that's not P in this thing here, and then there's a minus because it's 1 over P in the log, minus R log P. That's the only piece of S as a function of P and T that depends on P. And so if I work it out, I get minus, and then I get minus R over P, right? Whoops. I have just an R over P. So now I've shown that dV dt at constant P equals R over P equals R over P equals minus partial S partial P at constant T. So it worked given what we already know about the ideal gas, okay? So Maxwell's equation is true here. And why would I use Maxwell's equation when I could do something like that? Well, you don't always know all this stuff. And I hope you agree that this part was easy, and this part was harder. So it gives you these relationships give you alternative pathways to get things that you want. Okay. Now, we could spend a lot of time on this, but I don't want to do that, and you don't want to do it either. But I'm just going to give you a flavor of this thing about the partial derivatives and what you hold constant. Okay, so let's ask a question. So this could be a homework problem. This is an example in the book. So it's 3E.1b. I don't know. I don't like, this is terrible. It's like the VIN number of your car. You're never going to remember it. So how does the internal energy of a gas depend on volume at constant temperature? Now, I'm talking about, I said gas, but for the ideal gas, what is the answer? So I hold the temperature constant and I change the volume. How does the internal energy of an ideal gas change? It doesn't, right? So what I'm trying, so it doesn't. I couldn't have said it better myself. So we should get that. And so what this is like a word problem. Remember word problems? Yeah. In elementary school, my son, he was in some advanced class, and they gave him word problems, mathematics word problems that were very hard. And I was teaching graduate quantum mechanics at the time. And I kept telling the students in the class, my son, he's got these really hard problems. Oh, surely they can't be that hard. So, on the final exam, I gave one of these word problems to the, yeah, that was on the final exam in the graduate quantum mechanics course. But, okay, so this is a word problem. And so how do I translate that question into a mathematical expression? So what mathematical quantity tells me how the internal energy changes with respect to volume at constant temperature? So it's a change in internal energy, right? With respect to volume at what? Constant temperature. Okay, now, so this is the answer. What does that equal to? Well, I know that my U is a function of S and V, right? And I want, there's a V there, but there's the S. You know, the S is there. And I also know that U is like 3/2 RT for ideal gas. So partial U, partial V, at constant T equals 0 for the ideal gas. But I need to do it in general. So how am I going to do this? Okay, and this will give you the flavor. I'm not going to really ask you to perform this trick, okay, on an exam, but maybe some homework. So I know I have my U as a function of S and V. I know that my du is T, ds minus P dV, which is equal to partial U, partial S at constant V, ds minus partial, or plus partial U, partial V, constant S, dV. Now, I did my calisthenics. I said, I take a step this way. I go in this direction, which is a constant S. So I have this term here. That looks kind of like it's related to what I want, but I don't want to go in constant S. I want to go in constant T and see how the slope is different that way than that way, okay, at a given point. So, and this is your book doesn't do this, but I think this makes sense. So I'm going to take du, and I'm going to do it. This means I'm going to take a step at. This is not my Instagram. At constant T. Okay, so I'm just going to go through here. I'm going to say I have this thing, partial U, partial S at V, and I'm going to take ds at constant T. Okay. Plus partial U, partial V at constant S, and then dV at constant T. Okay, and so I have these three differentials, and let's just divide by dt. Is that what I want to do? No. Divide by dV at constant t. So you see what I'm doing? I'm constructing the thing I want by using what I know and using this sort of funky notation, which I hope makes sense. I'm gonna take these correlated steps. So if I want to take a step, let's belabor. One thing I'm good at is belaboring things, right? You have to admit that. Let's say I want to take a step du at constant t. This gives me an expression in the SV plane, or something, how to take that change. And so if I divide by dV at constant t, I'm going to get what I want. So du at t, dV at t is what I mean by that derivative, right? That's what I mean by this. let me clean this up. These notes are for posterity, aren't they? I mean, I will never be able to get them off the internet, right? They'll be on the dark web or something. That's what I mean by partial u, partial v, and constant t. And it's equal to partial u, partial s at constant v, partial s, partial v, at constant t, plus partial u, partial v, constant s. Isn't it? If you can read the subscripts. But I know this. Why do this? You know, I know this. And that's equal to t, right? And I know this. That's minus p, right? And so we saw earlier, this thing has already visited our house. We may not recognize it, but I'll remind you. I called it pi sub t equals partial u, partial v, at constant t. And it is equal to t partial s, partial v, constant t, minus p. This is a bit of a project. You know, I don't like wasting paper, so this will not be on the exam because I don't want to have a big couple blank pages. Okay, but you can see, you know, it is doable in some sense, but it takes time, and you know, this is the kind of problem that you bark up a tree a couple wrong times before you figure out, you know, what you're doing. But hopefully you eventually figure it out. So there's really two ways of proceeding. And, you know, why not just pick one way and get it over with? Because, you know, we're reviewing, we're trying to see this from all the angles and have like a complete, everything should work, you know, things are consistent. There's the problem with thermodynamics, in fact, is because it's all internally consistent, there are oftentimes more than one way to proceed, okay? And there's two ways. And, you know, under an exam condition, you know, I hope that, like, when I put a problem on the exam, there's these ones that take several steps. The good news about those are, you know, the steps are meant to lead you down one path, which is not necessarily the only one, but it's the one that's doable, okay? And you can tell me if these paths are equivalent or not. So the first way, I'll say, is from Maxwell's relations. So let's see if we can make some hay out of that, as they say back in Nebraska. I have, and what am I trying to proceed with? This thing, you know, I want to simplify. This is the problem strategy. I want to simplify that term. I know what T is. I know what P is. And you know, you know, I might say, you know, if this were a question given, express your answer in terms of T, P, and then, you know, whatever else it'll turn out to be. Okay. So we want to simplify that term right there, and let's see if we can do Maxwell's relations. So I look at that, and now I'm suggesting that you use the hints or the practical approach I give you. What Maxwell's relation should I use? And so first we have to check to see if we can use it. But whenever I see something like that, I'm immediately suspicious that Maxwell's relations could help. So, but which one? How do I choose what fundamental equation? And that's what we call them. Which fundamental equation should I turn to? So where's the first place to look? in the basement, right? So I see t and v. So that thing has underlying a t and a v as independent variables. So what function has t and v as its independent variables? Yes, Helmholtz. A as a function of t and v. Helmholtz. And I know that dA is if I'm looking on the front of the exam and I'm trying to remember it, but correct me if I'm wrong. That's dA for Helmholtz, right? And what that tells me is that S is or minus S equals. Where do I put the minus? It's a matter of style, and I don't really have a good style sense, so I go back and forth. But that's dA dt as a function of v, and minus p is dA dv as a function of t. And so my mixed partials. So I don't know yet. I mean, I could see it if I look at it, but I'm not sure yet if Maxwell's relations will work. But if they do, this is the place to start. And so this tells me that minus partial s partial v at constant t equals minus partial p partial t at constant v. I got lucky, didn't I? Because so therefore, I mean, let's show all steps, show all work. If I get rid of the minus sign, I can do that on both sides. I left it in, to try to give evidence, where things came from. So that's a relationship. So I've got, so that looks good. I've got P as a function of T and V, and I know, like for an ideal gas, that I know, and even for the van der Waals gas, you saw Craig 2.0, right? He went through that. Okay. So if we wanted to do that, we could, but let's not go there. Let's stick with the ideal gas. So I got lucky. That'll work. So I need to go back and say pi sub t equals, let me get it right. So I have the t partial p partial t at constant v minus p. So let's check ideal gas. P equals R T over V, right? Partial P, let's check it out. Partial P, partial T at constant V. So I take the right-hand side, RT over V. It's very simple. Don't let that stop you, okay? It's too easy. Yes, question? This was partial. This is thanks to this dude named Maxwell. Partial squared A partial T partial V equals partial squared A partial V partial T. Okay, so what I do is I go back here and I identify, this is the calculus. So now we just do calculus. Given this from the front of the exam, this I read off from that, because that's what I mean by dA is partial A partial T V dt plus partial A partial V T dV. That's what I mean by the differential. So I read these off, and then I use this to get this. And so I got, I was able to discard the inconvenient thing and replace it. and I have the structure of the mathematical universe to thank for this, right? And I replace it with something simpler. And so now I got that. So this is the it's highlighted. Okay, that's the answer in general. And you can go back to the Van der Waals gas and confirm that if you want. But let's check it for the ideal gas. So take the derivative of P equals RT over V with respect to T and constant V, and I get R over V. So pi sub T is T times R over V minus P. But what is RT over V? What is that, by the way? Well, RT over V is P, right? So that's equal to P minus P. And what's that equal to? What's the sign? Okay, is that positive or negative? Or is it equal to 0, right? I have to put the equal to 0. So I showed the thing that we already knew already, which was du dv constant T equals 0 for ideal gas. And because U is 3/2 RT. And if there ain't no V in there, there's just a T. Now T could be a function of V, but I'm holding T, whatever it is. Depending on the variables we use, it could be functions of other things, but I'm holding that thing constant, and everything else is a constant, right? So we prove that. And yes. It is 11, well, yes, it's almost 11:40. Do we have, Sarav, are you here? Does anybody know where Waldo is? Okay, we'll have to keep going because he's apparently not here yet. Yeah, anyway, let me just, let me do the other way and then we'll stop, okay? The second way, we can use S as a function of T and V, right? S as a function of T and V is S naught plus R log T over T naught to the 3/2 V over V naught. So partial S, partial V, constant T, which is what we have, is R over V, and then, etc. So that's another way we can do it. Both ways work. Which way is preferable? I don't know. You tell me. Okay. Interesting. I wonder if he knows where the lectures are. Okay, so yeah, questions. Yeah, sure. Okay, so yeah, I don't want to go on because it was getting questions. You want to know? Yeah, I'll do that. Hello. Good morning. Do you see Sarav? Go look for him. Yeah, I'll click that button and then you'll know. And do you actually want the exams back?
Right now would be great.
Right now?
Yeah.
Why not? Yeah, let's see. Now you have to realize that it takes me a while to deal with campus. Should I pack everything up? Do I have to make a quick getaway? Do you think? You realize that there's two-factor authentication that has to go on. Anybody know any good jokes? Okay, great. Transfer to web pages. It says it's published. Anybody see anything? Ah. So, I'm trying to publish the grades. All right, let's grab it. Okay, we're going to work in parallel here.